welcome to the third part on the series of videos about measuring lengths. So as a quick recap, in the first part, we discussed on how old units of measurement were used and what the problems were. Then we discussed how, in the second part, how the French Academy of Sciences decided to use something more natural like the earth itself in order to define the meter, and we went through that story. And we concluded by saying that today's way of measuring or defining meter is much different. And in this third part, we are finally ready for that. So let's begin. Now, we need to take a digression here and we need to actually discuss light in great detail. Okay? So if I take a ray of light and if I then zoom in at the smallest possible level as to what light looks like, it looks like this. It is a collection of oscillating magnetic and electric fields. So as you move along, if you freeze a ray of light, then along the frozen ray of light, you can see that there is at one place a high magnetic field, then it goes down to zero, then it becomes strong again in the opposite direction, and then again goes to zero. So the distance for a single ray of light where the magnetic fields or electric fields are zero at two consecutive locations, this is known as a wavelength of light. So, and our traditional light that we see every day, the sunlight largely, is a mixture of many wavelengths of light. And when you pass it through a prism, the prism has the property that it splits the light into multiple wavelengths. The red is the highest wavelength visible light, and the purple or the violet is the lowest wavelength visible light, and all the colors are in between. Okay. Now, if you take this light which is split, okay, and zoom in microscopically, you will find that certain wavelengths are actually missing. So if you see this spectrum of the sun, right? So this is sunlight which has been split into wavelengths and fully magnified. You will see that there are these bands, black lines, right? So these are missing wavelengths. The reason they are missing is because the elements in the sun have the property of absorbing specific wavelengths of light. And this whole science of using these missing wave bands to identify what kind of material we are looking at, what kind of atoms are present in the substance, is called spectroscopy. Next, light, because of its wave nature, exhibits something known as interference. So what we are doing here is we are taking a monochromatic source of light, which means a light source which is emitting light of exactly one wavelength, and then we are converting it into two sources. So the two slits that you see here are the blue big line, and there are two slits, so that now behaves like two sources of light, and the waves of this light interact. So when they hit the screen, on some places something known as constructive interference is happening, which means that the two waves are perfectly aligned with each other, so they add up and create a bigger wave. So you get a bright spot of light on that point on the screen where this happens. And then there are other points on the screen where the waves are out of phase, as we call them. So the lower part of the wave, it cancels the upper part of the wave and they zero out. So you get destructive interference, right? So if you see what the pattern actually looks like on the screen, it looks something like this. This is known as a interference pattern. It happens. So wherever you see these white bands, bright bands, that is where the two sources of light have fallen on each other in such a way that they are reinforcing each other. Where you see black bands, that is where the light has actually cancelled out, and you've gotten a dark band. Now, the study of optics tells us that the width of these bands depends on the wavelength of the light. So if you choose pure red light, you will get a different size of the bands. If you use pure blue light, which is a different wavelength, you will get a different width of the band. So what you can do is, if you give me a source of light, I can count the number of bands that are in it to tell what the wavelength is. Or in our case, what we want to do with the interference pattern is, we want to choose a known wavelength of light, construct a interference pattern using an experimental setup, and then we will define a meter as a certain number of bands. Okay, so if there are these many bands, then that distance is a meter. That is how the modern meter is defined. Now, what is the advantage of this? There is no bar, there is no painful measurement involved in, taking a bar, putting lines on it, comparing, nothing. Anyone, anywhere in the world can construct an instrument known as an interferometer, an instrument that basically can produce these patterns, choose an agreed upon source of light, and define the meter as number of bands produced by that wavelength of light. No physical handling of bars is involved here. That's the beauty of this manner of defining a unit of length. So in 1927, when all of this became clearer, the meter was defined as 1,553,164.13 wavelengths of cadmium. So you take cadmium, they assume that cadmium was a monochromatic or a single wavelength source of light. So you could then convert it into some number of bands, and you could use this definition to recover your meter. But the problem was that this became unpopular because the precision was lacking, and it was later found that cadmium is not a perfect monochromatic or a single wavelength source of light. Now you might ask, what's the big deal? Why should I only use a single wavelength monochromatic source of light? Well, the pattern that you see above here, the green pattern, is caused by a monochromatic source of light. When you have a mixture of colors, you get an interference pattern which looks like the one below. Now, I'm sure you will all agree that measuring the width of a band for the pattern below is very hard. And it is for this reason that we prefer a very highly monochromatic source of light. So in 1960, it was decided that instead of cadmium, we should use krypton 86 because the red-orange line emitted by krypton was highly monochromatic in nature. And so that was defined as 1,650,763.73 wavelengths of that light. And in terms of overall precision, this gave a better improvement. But then around the same time, lasers were developed and the precision became even more accurate. The precision became higher. And even this definition of meter started showing its limitations. In the meantime, our accuracy of measuring time was becoming really popular. So finally, modern science decided to define define meter in terms of distance traveled by light. So if you take the distance traveled by light in 1 second, and now this is modern era. So unlike the time when a pendulum could have been used, we did not know how to measure time accurately. But in the modern era, when we can measure time more accurately, we know how to measure 1 second very accurately. We allow light to travel a distance, and that distance divided by 299,792 2,458 parts, that one part of that distance is a meter. And that is how we have finally reached the modern definition of the meter, which is defined in terms of how much distance light covers in 1 second. Okay, so let's wind this up by talking about what happens in India. So there is an institute known as the National Physical Laboratory, which is in charge of maintaining the standards of length in our country. And the National Physical Laboratory will interact with BIPM and other international labs at the international level. And at the state level, there are some state centers with which this interaction takes place. And any manufacturer of instruments has to calibrate against the state centers. So this is what happens in India as far as standardization of any measurement is concerned. Now remember, we've only covered a very detailed, I would argue not so detailed, but an overview of the history of the unit of length, which is meter. There are 6 other fundamental units that we use in physics. There's the kilogram, there's the second, there's the ampere, there's the Kelvin, there's the mole, and there's the candela. Each one has a history of their own. We have already seen how fascinating the history of length is. I'm sure the histories of all these other units are equally fascinating. So with this, we conclude the series, the 3-part video on measuring lengths. I hope you enjoyed that, and I look forward to creating more such videos where I take my lectures from the past and then convert them into accessible YouTube videos. Thank you so much.